So this problem may have tripped you up a little bit. If it did, don't feel too bad. There's a lot of parts on this, and if you don't remember some of the equations, it requires a little bit of extra work. When I'm looking at this problem, first thing I want to do is read it. So I'm going to get a projectile is fired straight up from the Earth's surface with a speed that is half the escape speed. If r is the radius of the Earth, the highest altitude that it reached measured from the surface is what? I'm going to underline measured from the surface because I know that I always want to deal with universal gravity where I'm dealing with the distances measured from the center of the Earth, not from the Earth's surface. So I want to make sure that I don't screw this up. And actually, to be even more clear, I'm at a height h that I'm going up. My v initial is equal to v escape over 2, going with half my escape velocity. And just so I remember, I have radius of the Earth in here. And actually, that value should just be r. All right, let's go ahead, work this problem out. And I think we have to do this in 2 parts because I don't know what the escape velocity is. So I'm going to figure out what the escape velocity is first. So v escape is equal to what? Can I give it to can I get myself a value for this escape velocity in values that are given here or ones that I think are going to be easier to use? So let's say we have an object with little m and the Earth has big M. So my escape velocity, I remember, comes up from a conservation of energy equation. The initial kinetic energy plus the initial potential energy is equal to the final kinetic energy plus the final potential energy. In order for me to get escape velocity, I know that my final potential energy is equal to 0. Why do I know this? Well, I know this because my value for u, gmm over r, that at my potential energy is 0, I'm at a distance of infinitely far away from my original mass. They're infinite distance separation. And that's what the idea is of that's what the idea is of escape velocity, is where I give myself just the minimum amount of energy, or initial amount of kinetic energy, to change my potential energy to go from some value to a value of 0. So I'm going to start at the Earth's surface, and that's going to equal 0 kinetic energy at the end because I don't want to give myself extra energy. The definition of potential energy is the minimum amount of energy to get there, minimum velocity to get there. And I know at the very end I end up at 0 potential. So my mass of my object cancels out, and I will see that my v escape is equal to 2 gm over re, radius of the Earth. Actually, I keep wanting to put the radius of the Earth in, but I labeled it r, and that's a squared value. So that means I could take the square root, but I can just put the square root in later. So I'm going to save myself one line. I'm going to move on to the other part. So the other part is figuring out how high does it go when I'm at half the escape velocity. So again, k initial plus u initial is equal to k final plus u final. So my initial kinetic energy is 1/2 little m v escape over 2 quantity squared. Right, that's what it tells me. Leave this thing with an escape velocity with half my escape velocity. To that, I'm going to add in my initial potential energy, big M little m over r. My final kinetic energy, well, I'm not doing an orbit, I'm just going straight up. So like the problems where we had a hill and we give ourselves an initial velocity and we go, how far up the hill do we go? I know at the end, when I get to the highest point, my velocity is going to be 0 at the top. So in that case, v final equals 0, which gives me my kinetic energy equals 0. And last but not least, my potential energy, gmm over a height of h. plus RE, or plus R. I'm at a distance from the Earth's center of R plus H above. So I took into account that I'm measuring from the surface with H, the value I actually want, but the real value that I get out is, or the real value that I need is H plus R. Again, little m is going to cancel in all these cases. So I get 1/2 times 1/4 V escape squared. I'm going to move, I want to keep this on the same side, minus G big M over R is going to be equal to big G big M over H plus R. All right, I'm going to plug in my value for my escape velocity. I need the velocity of escape squared. I have the velocity of escape squared here, so I get 1/8, these two values together, times 2gm over r minus a gm over r is equal to a gm over h plus r. This is a factor of gm, that's a factor of gm, and that's a factor of gm. So my gravity and my mass of the Earth actually drop out. And I am left with 1/4 1 over r minus 1 over r, oh, there's a minus sign that I forgot, is equal to minus 1 over h plus r. And I'm running out of room. I grab another piece of paper, just shift everything up a little bit. So I get, I'm going to multiply through by minus 1 on all my things, on all my terms, just to make it so I have more positive. So I have one value of 1 over r and a quarter value, so that gives me 3/4 1 over r's is equal to 1 over h plus r. And at this point, I'm going to multiply or flip my equation by inverting it. So I get 4/3 r is equal to h plus r, 4/3 minus 1 r is equal to h, and this gives me that h is equal to 1/3 times r. So if I'm at half my escape velocity, I'm going to go 1/3 radius of the Earth higher than where I started. So if I actually look back at my original page, I get my value of the radius, 1/3 the radius of r above the Earth's surface. So back to my picture, my h is 1/3 above it. So pretty easy problem to go through. I needed to figure out what my escape velocity was first, because I didn't know that in terms of values that I needed. But I really solved conservation of energy. Initial kinetic energy, initial potential energy. I ended with final kinetic energy of 0 because I was at a highest point, and I calculated my final potential energy. Then it's just a matter of working through the algebra and not making mistakes.